Hello everyone, good afternoon or good evening or good morning in my case. This is Yoni Nazarethi here from One on Epsilon, and we're in the 4th edition of Math Teachers Code. So today we'll be doing exploring number bases, base representation of numbers and such. And we'll see how to code such things as well. So before anything else, I'll go to JuliaBox, where we'll be working and where the previous sessions have taken place too. And I'll log in with email to JuliaBox. I'm using the Math Teachers Code email in this case. And I'm logging into JuliaBox. So if you haven't done this before, you can watch some of our previous videos and see how to log into JuliaBox. It's simple. You can make an account. There's a free account. That's the one we're using now. If you have, you might want to just follow along and do it live. So I launch JuliaBox, and that creates an instance of my environments somewhere in the cloud, somewhere on Julia Computing's servers. And in a second we'll start our notebook, which we'll work with. Let this set up for a second. So this is the Jupyter environment. We've spoken about this before. I've used this quite a lot for teaching, for live teaching, and one of the purposes of this series is to show you how you can use this for teaching as well. So all you need is a web browser, nothing more. So I'm going to create a new Julia 1.0 notebook. And we will call it, just like we did to the previous sessions, I change the name, I click the Untitled up here, and I'll call it Math Teachers Code Session number 4. And that renamed this notebook. And if I go back to the other tab, I can see that I have this Math Teachers Code Session number 4. By the way, the previous sessions, as will this session as well, you can go to the description of the YouTube video and get the notebook Julia code either in PDF format or in this format, which is a Jupyter notebook, which you can then upload to your JuliaBox. That's an IPYNB format. That's a Jupyter notebook format. Okay, so we're here, and before we do anything else, let's actually start with something a bit obscure, a bit obscure, but kind of fun. So I'm going to change the cell to a markdown cell. I did this by hitting the M button. I could have also gone here and changed it from a code to a markdown cell. This is just a cell where we're going to write stuff, and I'll put it's a question by a fella called James Tanton, and that's his Twitter handle, from October 9, 2018. Okay, if I hit Shift Enter, this cell is formatted, this markdown is formatted. So this happened to be during the Global Math Week. This is a website for the Global Math Week or Global Math Project. I'll speak about this in a few minutes more. But Dr. James Tanton asked the following. He wrote, n has one digit in base n plus 1 and more digits in base 2. Well, in another basis, there are also potentially more digits. And let an be the average, the meaning is the arithmetic average in this case, number of digits of n when represented in bases 2, 3, etc., up to base n plus 1. Graph, bounds, limits. I'll hit Shift Enter to see this formatted. So this I thought was a quite nifty question. Let's unpack it. So n, the number n is some number, and if we treat the number n in base n plus 1, so in a base that's bigger than the number, then it only has one digit. Let's just see an example. So the number 9, for example, if n equals 9, has only one digit in base 9 plus 1, which is 10, base 10, which is what we use, right? So in base 10, the number 9 has only a single digit. But, you know, number 9 in base 2, it has more digits. It has like, it requires more digits than that to represent. Okay. And an is the average number of digits when we represent this number in base 2 or 3 or 4 of n plus 1. So you take the number n and then you look at its base representation from base 2, from binary, up to base n plus 1, and you count the number of digits that it has in each of these representations, and then you do the average, and that's this a of n. So for every n there is an a of n. A stands here for average or something like that. And it's something a bit obscure, but there's some questions coming from it. Is this the most important question in the world? Probably not, but students thinking about it, sure, it can be interesting and kind of fun. So what we're going to do now is actually use some, quote, heavy machinery in Julia to just look at a of n for a few different numbers. So for this we're going to use the digits function. So later on today we're going to, in the session today, we're actually going to code some things from first principles, but let's look at the digits function. So I do question mark digit, and the digits function, you can put a number into the digits function and you get an array of the digits. That's pretty much what digits does. For example, digits of the number 209 gives us the digits of 209 as an array, and the first element of the array is actually 9, the second is 0, and the third is 2. Okay. If we would have wanted it in a different base, so this was by default in base 10, so the base argument is by default 10, so we actually don't need to represent that. But we could have also said, let's say digits of 9 in base equals 2, and this is how you do 9 in base 2. So what this is, I'll change this into a markdown cell. 9 in base 2 is 1001. Okay, that's 9 in base 2. Because this one here is with a weight of 0 or 1. This 0 is with a weight of 2. This 0 here is with a weight of 4. And this 1 here is with a weight of 8. So 8 plus 1 is 9. Okay. So that's a digits. That's a digits function. Okay, we're actually going to do this ourselves soon. We're going to create such a digits function ourselves. But at first, let's use the built-in Julia one. All right. So what we want here is we want to take a number n. Okay, so we want to take n as some number, and we want to look at the digits of n with some given base. Okay, and we want to look, according to the question, at all bases, base 2, 3, up to all bases up to base n plus 1. Okay, so how do we express this thing in Julia? How do we express this thing in Julia? Well, one thing we can start with is we can create a comprehension. That's something we did last week, and it's a basic thing in Julia. So we're going to create digits of n. There's going to be an n. And for now, let me just take our n to be, for example, the number 209. Okay, or let's choose something smaller, like 26 maybe. The digits of 26 would base be for b in 1 to n plus 1, which is 27. If I now run this cell, what I've created, base going from 2. So I got an error, domain with 1. The base cannot be, you can't have a number in base 1. You have to be in base 2 or above. So base 2 to 27. So this is now an array of arrays where for each time I got the digits. This is how you represent 2 in base. This is how you represent 26 in base 2. This is how you represent 26 in base 3. This is how you represent 26 in base 4. Let's just see. Let's see that 221 is 26 represented in base 4. So I'm going to just evaluate this manually. 221 in base 4 is 26 in base 10. Let's check. So we've got the 1 times 4 to the power 0, okay, meaning just the 1, plus 2 times 4 to the power 1, plus 2 times 16. Does that equal 26? So let's just do this in our 221, 26 in base, sorry, 2, 3, 4, yeah, 221. So 1 plus 8 is 9 plus, sorry, the 116. That's my mistake. It's a 1 times a 16 and a 2. What am I doing? So 2 to 1, am I reading this correctly? 2 to 1, 2 times this, yeah. So 2 times 1, that's a 2, plus a 2 times 4, that's an 8, plus a 1 times 16, and that's a 26. So I got confused with the order there. Okay. Because we're reading it left to right. All right, so we've got here for the number 26, we've got its representation in every base. We've got the representation in every base up to base 27. Now, instead of actually looking at the digits, let's just change this line and do the length of this thing. Okay, so I'm doing the composition of the function length on the output of the function digits, and that's actually going to give us the length. So we see that's the number of digits needed for the number 26 in base 2. And this is the number 3, is the number of digits needed for the number of 26 in base 3, etc., 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 up to this final one, because 26 in base 27 requires only 1 digit. Okay, so if we had this, now let us calculate the average of this. For this, let's use the mean function from the statistics package. I don't think we've done this before, so I'll do using statistics, and then I could use the mean function. The mean is just an arithmetic mean function. So mean applied to this array would calculate the arithmetic mean of this array. Let's do this. And we've got some mean value. It turned out that on average, the answer to this question for capital N equals 26, when capital N is 26, then the average value was put 2.19. So let's make this a function. Instead of just thinking about 26, let's think about any possible number, and let's just call this a function, just like as was in James Tanton's question, and we'll call that function A. So A of n equals the mean here, where we're going to look at the digits of n, so I'm replacing 26 by n, and this 27 is n plus 1. So we're running on the base from 2 to n plus 1. And I evaluate this cell. Again, we evaluate cells in Jupyter by hitting Shift Enter. That's how we evaluate cells. Okay, so I can then do, for example, A of 26, as we did, and that's 2.19. Okay. So let's plot A of n as a function of n. And let's see if we see some patterns. So initially this thing looks completely obscure, but it's actually some quite neat little investigation which you can do with your students, maybe with slightly more advanced students. So let's plot, let me actually also use the pyplot package, because we're going to do plotting. Okay, and I will plot let's say the numbers from going on the number from 1 to 10, A apply to those numbers 1 to 10. Now what I'm doing here, I'll go to the cell below and show you again. So when I do A apply to, for example, 2, 3, and 9, this applies, this dot broadcasts the function A. It maps the function A onto 2, 3, and 9. So I'm getting A of 2, 3, and 9. That's how this thing works. That says A dot 2, 3, 9. So here I'm going to do A on the whole range 1 to 10. Okay, I'll delete the cell below. Let's do that. By the way, to delete cells, I hit the escape key and then hit the X key. And that's how, once a cell is selected. Okay, so what we're seeing here is for every value up to 1 to 10, we're seeing A of n. And so far, it doesn't look so interesting. Now, let's not connect this plot with a line, so I'll put another argument to the plot function, comma, and in quotes, I'll put a dot, and that just tells it to plot dots. But let's not go to 10, let's go to 20. Let's look at the first 20 values of the function A of n. Oh, something appears to emerge here. Let's make another variable, and we'll call that variable maybe nmax, just the name of the variable, and let's set that variable now to 100 and plot up to nmax. So now some pattern seems to emerge. So when we go on the horizontal axis from n going 1 to 100, the average number of digits representing each of those numbers from base, when we take the average from base 2 up to base n plus 1, appears to have this, well, there's some jumps that occur there, but appears to be somewhere around, well, just above 2. What if we were to increase this to 1,000? And we might need to wait for a sec. It didn't take too long. We see that there's this initial behavior, which is kind of less than 2. But then this thing appears to go down and down and down and down, and I wonder if asymptotically, as n goes to infinity, does A of n go to 2? So one thing I can do is I can actually look at A 10,000. Well, let's just do A 10 to the 4. 10 to the 4. A 10,000. Oh, and I get a value that's quite close to 2. Well, how about A 20,000? Seems closer to 2. A 30,000 seems even closer to 2. So just looking at this graph, I believe the following. I'm willing to conjecture the following, and it's I'd love if anybody there would want to prove this and post about it, retweet, tweet. Let me know that the limit of n to infinity of A of n actually equals 2. Okay. What I did here is I wrote LaTeX in a markdown cell. So I hit escape, I chose a cell, I changed it to markdown. That's up here. You can change it from code to markdown, and then that is my belief. Just to have a bit more numerical evidence for this belief, let's actually look at A of n minus 2, so the deviation from 2. Say for n in, let's say from 100 to 10,000. So this is a comprehension of the deviation of A of n from 2, and let's call this the errors. Okay, and then if we plot 100 to 10,000 over errors, and then what this is going to do is, you see these errors get smaller and smaller and smaller, and we believe that this actually converges to 0, or at least I believe. This is actually not so hard to experiment with, to try, to write out analytically. But I challenge you to prove this conjecture, and or to say other interesting things about A of n. Okay, so I started today with rather obscure question because I wanted to show something a bit interesting and something that is kind of out there. And now I actually want to step back a few steps and just go to the basics of base representation of numbers and also show how this is done in Julia. And this is also relevant to other programming languages as well. Okay, so as an example, let's now take a maybe not such a small number. Let's take like this. What is this? 65,204. And let's consider it in base 16. Okay, in base 16. So base 16, that's sometimes called hexadecimal. Okay, so if I would now do the digits of this number where the base equals this b, 16, we're going to get the list representing this number. Now, what we got here is the first digit is 4, and the second digit is 11. Now, in hexadecimal, what you actually do with 11 is I'll write this again in the markdown cell. So hexadecimal base 16 is often used in computer programming, and the digits are then 0, 1, 2, 3, etc. up to 9. And then they continue. The value of 10 is the digit A, and 11 is B, and 12 is C, 13 is D, 14 is E, and 15 is F. Okay, so that's hex. Okay, this is how we do hex. All right. So these are the digits of this number in hexadecimal. Now you can actually, and there are many uses for this in computer coding. You can actually represent a number using hex, and you can do it using 0x, and then you would put the number in x. So for example, if I write the number 11, that just means 11 in base 10. But if I do 0x11, that actually means 11 in base 16, which should be 1 times 16, which is 16 plus 1, which should be 17. Okay, so let's just see this. So if I do 11 minus 17, I'm going to get a 0, right? Or if I do 11 minus 1, it's 16. When I just wrote 0x11, I saw the printout of this literal was still represented in base 16, but still it's the number 17 if we would like. Okay, or the number FF, which is a very common number, that is nothing but 255. So if I do, for example, just to show you, if I do 2FF minus 254, we're going to get 1. Okay, or FF plus 1, it's going to give us 256. So once we add the number, and if we add it here in decimal form, then the output representation is in decimal form. Now to see that this digit thing worked, let's actually try to see what 65,204 is. So we're going to write 0x, the 15 is a F, that's this 15. The 14 is a D. The 11 is a B, and the 4 is a 4. Let's hope this works. And I guess if I don't know exactly how to print it as a non-decimal, so I'll hack it. I'll do a minus 1 plus 1, and we didn't get exactly what I expected. And what did I do wrong? So 15, 14, 11 is a B. FDB4. Did I flip the digits again? Is it 4BFD? I think it probably is. Nope. I'm now in guessing. So what we got is we said 65,204 in base 16, and we got a 4, 11, 14, and 15. So let's see how I would get out of this trouble that I got into. So I'm just going to choose a smaller number. So we'll choose this one that we like, and that's the number 17. Well, maybe 17 is a bad example. Let's choose 18. So with 18, we get a 1, 2. So I see that this 2, this first element of the array, that's the LSD, the least significant digit, and this 1 is the most significant digit. Okay, so again here with 65, 204, I've got a 4, 11, 4, and 15. And then I'll go back and try it again. So the 15 we believe is an F, and the 14 we believe is a, oh, that was my mistake. It's not an E, it's a D. Sorry, it's not a D, it's an E. It's an E, B, 4. And there we get our number. Okay, so I just made a mistake and I went to the D instead of the E. Okay, so I'm kind of moving all over the place here. But the point is that we can use the digits function to represent things like that. Now let's actually systematically see that for any n and any b that we get, this digits function gives us what we want. So let's actually use this thing and to represent the number based on its digits. So how do we do this? So one thing we can do is we can, let's just call the result of digits, we'll call this dig. Okay, so dig is this array. All right, so that's the answer, the output of the digit function is in dig. Okay, you see that's dig. I'm going to delete this dig now, and here it is, it's this dig. So if I would take dig and go from the kth digit, and I'm going to go for k in 1 to length of dig. Okay, so this comprehension gives me the digits. So far it didn't do anything. But if I would take this digit and I would multiply it by the base to the power k minus 1, then this is actually the base representation of numbers. This is a base representation of numbers. So what this is actually saying is, I'll do this in Markdown, it's doing the d sub k multiplied by b to the power k minus 1. Oh, sorry, I'll do this as a LaTeX cell, like that. Okay, so this is the term associated with the kth digit with base b. Now, what is the base representation of numbers? It's the sum of these terms with k going from 1 to the number of digits. Okay, that is the base representation of numbers. So let's actually do this sum. Let's just sum this thing up. Okay, let's just sum this thing up. And you see, when we sum this thing up, we get our number back again. So for example, if the number was something completely different, this, and it was in base 13, no problem. We've unpacked it into dig. Let's look at the intermediate output of dig. I'll actually just do println dig. Println, not printn, println dig. And it turns out that in base 13, the representation of this number is 57721. And if I now use these and use this formula up here, so that is the number equals that, then I'm getting the number again. And we can do this in any base and stay happy. All right, so that is one thing I wanted to show, which is just the basics of base representation of numbers. There's also note that you can do something like this. You can do, for example, you can use a parse command, so $parse. And what parse is you give parse what you want to parse, and you actually give it a string, and you say in what base you want to parse it, and it will convert it back into a number. So, for example, we know that 577, let's not go for base 13. Let's take this example and go here for, let's say, base 8. So base 8, by the way, is called octal. So this number, 34,234, in octal is the number 276201, but it's actually, keep in mind, again, we're reversing it just to see that it's actually 102672. We need to read it from right to left. Okay, so this here is the digit with the lowest weight. Let's try and see this via the parse command. So what we're going to do is we're going to parse into an integer. We're going to take the number 102672. So I've put this number as a string, okay? And I'll say base equals 8. And you see, if somebody would give us this string, we've parsed this string to get this number, 34,234. Okay, what parse effectively did, in addition to a whole bunch of error checking and format changing and stuff like that, it pretty much evaluated this type of code. That's what parse did. Another small thing to know is you can ask the bit string of some numbers. So if you look, for example, at the bit string of the number 19, so this gives us now the bits that make up the number 19. Now it's padded with a whole bunch of zeros because this is how the number 19 is represented in memory. Okay, the key point here is that 19 is 10011. Okay, that is 16 plus 2 plus 1. 16 plus 3, that's 19 in binary. Okay. Now, if you go to the Julia documentation and look under numbers, you'll see a whole bunch of other things associated with bit strings, with parse, with digits. So we basically use these three built-in functions, parse, digits, and bit string. Okay, and this concludes the first part of what I wanted to do today, which is kind of touch the basics of base representational numbers. And now I want to move on to the second part. And in this second part, I want to speak about exploding dots and the global math project. So first of all, if you head on to Epsilon Stream, so epsilonstream.com, and if you just key in exploding dots in Epsilon Stream, we've linked a whole bunch of resources associated with exploding dots directly in Epsilon Stream. So you can do stuff that is completely not related to exploding dots. For example, you can go and ask for, you can say, the base representation of numbers, okay, and see a whole bunch of nice things that we've curated for base representation of numbers. But then you'll also get a link into exploding dots and see number bases with exploding dots. So what is exploding dots? Exploding dots is this system suggested by Dr. James Tanton and many others, and advocated by the Global Math Project. And it's a system for playing around with numbers, their representations in different bases, and actually understanding arithmetic fully via these such number systems and via this representation. So let me try and explain that, and you could just watch one or two introductory videos. So if you go to the Exploding Dots home, you'll see some very cool introductory videos about exploding dots. And as a math teacher, you can get this very, very quickly. So the key idea in exploding dots is something called the NK machine. Now, the way this machine works is you kind of have these slots, which I'm drawing now. And this machine creates some transformation where if you have some, putting a few dots in a slot, and maybe a few dots in some other slots, and think of the slots as going from right to left, okay? So the rightmost slot is the least significant digit, and the leftmost slot is the most significant digit, but you don't have to think of it just like that, per se. What the NK machine does, it is a transformation on such an array of slots where if you have any n dots that appear here, explode and become a single dot on the machine, on the slot on the right, on the left of it, on the next slot. So the most common machine is actually an N1 machine, and specifically, let's say a 10-1 machine, which is the base 10 machine, or maybe the 2-1 machine, which is the binary machine. So let's look, for example, at the 2-1 machine and just do this visually. So if we take the 2-1 machine and start here with 3 dots, so this is actually the quantity 3. We have 3 fingers. Okay, we have three things. We have, yeah, I guess three things, sure. So we've got these three dots here. These two, which I'm highlighting now, kaboof, explode and go here. And at this point, there are no more explosions, and the system has reached some resting point. There's no more explosions. And what you get is the base 2 representation of the number 3. Okay? Just to see that this works, let's say if we had 5 dots, 1, 2, 3, 4, 5. So these two, say, would explode and would come here. And then there'd be another explosion. These two would explode and come here. Oh, but then in the second slot, there's also 2 dots, and they see each other and explode and come here. And indeed, if you want to look at the bit string of the number 5, of course, you've got a 1 and a 1 and a 0. So this 1, 0, 1 matches this thing, right? And the rest of the zeros to the left, as we have here, as we highlight here and go on forever, are just paddings. Okay, so that's exploding dots. It's a very simple concept, but it's actually an incredibly beautiful concept. So you can use it to, first of all, understand numbers in different bases, but you can also use it to understand base 10 numbers pretty well, which is what most of us think of, certainly in elementary mathematics. Okay, so if you have here now more than 10 dots, any 10, if this was now a 10-1 machine, any 10 would explode. And then, so let's say, I'm not sure if I highlighted exactly 10, but something like this, and then move here. Okay? And then you'd get the number, for example, 12. You can do arithmetic with it. You can understand all of the arithmetic algorithms that are taught in primary school with it. You can even do irrational numbers and play with them. And you can also do some aspects of algebra, specifically polynomial arithmetic with it. So that's exploding dots. So let's now write code that kind of does this. Now I must say, if you go to the global math project page, you'll see a link. So if you click this thing, 2018 exploding dots, you'll see a link to the exploding dots experience, and there's some wonderful experiences that have been coded for you. And many people around the globe are playing with this, and go ahead and try it. So try this stuff. So you see 5 million plus participants have done this type of stuff. But we want to say that this has been done by you or your students, and now you actually want to code this with them. We want to see how you can code such a thing. How you can simulate these explosions, and we'll see that this is actually a one way of implementing an algorithm of changing from one base to another. Okay, so what we want is a way to take this array and apply explosions to it. Okay, so take the array and apply explosions to it. Now, to do a robust, full implementation of this might take a bit of time, so let's go for something that's kind of halfway-ish, but it should still do something. So let's set the number m to be 5, and by this we'll say the number of bins. Okay, so one of the things we would want to do in a full implementation is to actually grow our array and grow the number of slots, the number of bins and exploding dots, if needed. But now let's just take a fixed number of bins. Just like here, there are, I think, 64 or 32 bins, 64 bits. Okay, so we'll take m to be 5. And let's take our base, let's think of base 10 first. And what we'd want to do is we'd want to take a function that takes such an array and explodes it if needed, but only does one explosion. So we want to see one explosion at a time. So let's call this function, well, let's just call it explode. And what this function does, it takes an array, okay, which represents this type of thing, and creates explosions. Okay. Now, how is this thing going to happen? Well, let's loop on the indices of the array. So we'll let I be the index, or we can use k if we'd like, and we let it be from 1 to m minus 1. So the reason I'm saying m minus 1 is we'll assume, well, we're not going to do explosions in the last bin because then we'll have an overflow. So our assumption here, which is wrong if m is too small relative to the values of the array, is that explosions won't overflow out of the array. So we're not going to do any explosions in the last cell. Okay. And what we're going to do is we're going to search for values that need explosion, that in the array that require explosion. So how do we do that? So what we can ask, we can say if the array at the case slot is greater or equal than b. What does that mean? The array of the k slot is greater or equal than b. That actually means that we can make an explosion in that array. Then let's write code here for do an explosion and quit. So how do we do an explosion? Well, an explosion is to take those b elements in that array, in that slot of the array, and take them away. So we can say array k minus b. So they've just disappeared from that slot. Now a slightly nicer way to do this, to write this, is not array k equals array k minus b, but array k minus equals b. These things are equivalent. Okay, that means array k minus equals b, take away b from array k. That's common notation even back from the C programming language. And what happened to those b dots that exploded? Well, they've moved from slot k, they've moved from slot k to slot k plus 1. So then we'll say array at slot k plus 1 plus equals how many? Well, we're talking about the b1. Okay, this is, by the way, this is the b1 machine. Okay, we're not doing any b not 1 machines in this case, but of course you can if you get the point of this. So we're going to add 1. So those b dots from array k have exploded. In array k plus 1, they've grown to be there. Now if that happened, we want to stop. We want to stop. So let's return our array. Okay, let's return our array. And if it doesn't happen, so if we looped and there were no explosions, so we loop, we loop, we loop, we loop, we loop, and then there are no explosions, we'll also just return the array. Okay, so this is a function explode. Now, there is a bit of an issue with this function, and this is a slight technical issue associated with Julia. It's an important issue, and that's the fact that arrays are passed into functions by reference. That means that if we were to pass a function array into the array r into explode, whatever we pass in explode will actually change that array. For simplicity, we don't want to do this, so let's actually create a new array, and that will be a copy of that array. So this creates a copy of the array so we can work on it. Okay. You're welcome to look at the documentation for the copy function and for passing of values to functions by reference or by value and see the differences. But that's all that's needed for now. So any changes that we do, let's actually make them on new array. Okay. And this is our function explode. Let's run the cell. Shift enter, and we've got explode generic function with one method. This one method means that if we do methods of explode, so there is one implementation of explode, one method that takes an array. We could have taken different forms of the function, all with the same name, explode, and potentially with different argument types, and then we'll have more than one method. So just so you see this, you can do, for example, if you do methods of rand, we spoke a lot about the function rand before. You see rand has 64 methods. You can do rand in different ways. Okay, But that's a bit of a digression. I'm going to delete this cell, and do an explosion on the array. Let's take the array 12 to 11, 0, 0. Okay. So what happened here? So we started, now this 12 actually, this is a bit confusing, it's from left to right, but this 12 is the least significant, which in our way of illustration is the rightmost cell. Okay, so there are 12 dots here, and then there's 2 dots and 11 dots and 0 dots and 0 dots. So what did explode do? Well, those 12 dots, we know that those 12, 10 of them exploded and went away. So then only 2 are left. And what happened when those 10 went away? That 2 is no longer a 2, but is rather a 3. Now, could more explosions take place here? I think yes. So if I would now do explode on this, so explode on explode, so do the function composition of explosion on another explode, shift enter. Then now this 2, 3, 11, 0, 0, you see this 11 here exploded, and we've got a 1, 1. So in the 10, 1 machine, when we started with this number, we've got 1, 1, 3, 2. Okay. Well, how about, what if we were to start with explode on something like 280, 212, or 213? And to do this, I'll do 2, 1, 3, 0, 0. Again, this 0, 0 is because we're forcing the function to work with arrays of length 5. So we're working here with fixed length arrays. So if I do, sorry, what I meant is 213 here, and then put a 0 and 0 here. So now I'm putting all of my dots, all the 213 dots in the first cell, and creating an explosion from that. So you see there was the explosion of 10 dots and from 213, and we moved there. So let's do explode on out 54. So out 54 is a return value of that. And there was another explosion. And let's do explode on out 55. And there were more explosions, etc., etc. And of course we can continue this. And if we continue this enough, we actually expect to see the base 10 representation of the number 230. So let's actually write code that creates this for us, that loops on explode until there are no more explosions to do. So we're speaking about base 10. We're speaking about an array, which our initial array for this example was, for example, this 213. And we are going to then loop and explode. So we will loop essentially forever while true. This while true loops forever until there's no reason to loop anymore. Okay, so while true, if I just run this now, the kernel is going to get stuck, and because the condition true is always true, and between lines 3 and 5 we're always going to run. But basically what we're going to do is we're going to do the following. We're going to say new array equals explode of the array, and then we'll ask if new array was equal to the array. Now the logical equals is equals equals, okay? If the new array was equal to the array, that means there were no explosions, okay? So the system has reached rest. No more explosions, we will break. This break stops the loop. Otherwise we don't break, but we'll just keep the array to be the new array. Okay, so let's analyze how this thing works. So we start in line 2 where we have an array. Then in line 3 we're saying, well, let's just continue between line 9 and 3 forever unless we break in line 6. In line 4 we're going to create a new array. We're going to apply the function explode to array. And then we're going to check, was there actually an explosion? If not, and this is not, if no explosion, right? Because No explosion means that new array was actually equal to array. There was nothing to explode. Then we'll break and we quit. Otherwise, we'll continue and we'll set the array was a new array, and the thing loops around. Now the only thing we might want to add here is we'll add a println of the array. Okay, maybe it's better to do it here. Like that. So then every time as we start an iteration, we're going to print the array. Let's try it. So we started with 213, and then there was an explosion. And then there was another 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 explosion. Now, kids all over the world that have done exploding dots in various ways on the blackboard in different countries using online tools with their parents, with their teachers, etc., have done this. I don't know how many have actually coded this. So here you're actually seeing the first explosion, the second explosion, the third explosion, the fourth explosion, etc., etc. And then look, once these explosions on the first cell were done, what happened here? There was now an explosion of this 21, and kaboof, it became a 1. And this 11 became a 2. And that was it. So this allows us to actually find the digits of the number 213. Okay, they are 3, 1, 2. Okay, they're given here in reverse order. Just to see that this that we're happy with this, let's look at, for example, base 2 of the number 19, which we looked at before. So this is now going to be the 2-1 machine, and let's run this. And we get explosions, 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 and then we get the base 2 representation of 19. So let's do, what did we call this? What was this command called? The bit string of 19 is 11001, and that's this 11001. Keep in mind we were on shaky ground here with 19 because the capital M, which was 5, if we would have gone to anything bigger, well, anything actually greater or equal than 32, we would have an overflow. So we should increase this M. So clearly this is not a robust piece of code, but it's a piece of code that if you do this with your students, perhaps live, perhaps semi-live, perhaps in a different way, then they can actually code the explosions themselves. So some challenges for you. Try to take this explode function and modify it a bit and make a general function which is convert from a number 1 in base 1 into new base. Okay, so try to make a function that takes an array number 1 in base 1, a base, and returns an array of digits in new base. Okay. You can do this using this explode function. It's by no way the most efficient way to implement such a base conversion function between bases. But it's kind of neat because it utilizes exploding dots. Okay, so I'm Yoni Nazarathi here. I think I'll quit for this session. I'll remind you that you can visit us in Epsilon stream. Please register with us. Like this video if you like it. Subscribe to our YouTube channel. And most importantly, try Epsilon stream. So with Epsilon stream, you can key in any term in the world of primary, secondary, or exploratory mathematics and get incredible content that our team has chosen for you. So you can go for anything in this realm and see what we have curated for you. And the point is that we've taken a whole bunch of content from YouTube and elsewhere in the web and really searched for the best content, and we're continuing to improve this experience. Okay, see you next time, and bye-bye.